Laura here for the first talk this morning. She will talk about studying the jet core with jet substructure.
Cool, thank you. All right, that sound okay if I'm here still? Cool. All right, so hi, everyone. First, I just wanted to say thank you to the organizers for inviting me to give this talk. It's been super wonderful to see all of y'all in person again after so long. But yeah, so today I was tasked with giving a talk on how we study the core of the jet with jet substructure. So when we talk about measuring jet substructure in heavy ion collisions, what we typically do is we construct different observables that are sensitive to different aspects of the jet substructure modification. So first, we can talk about observables that look at the distribution of final state hadrons inside the jet. And so as Ray and Martin already talked to us a lot about yesterday, these tend to be sensitive to things like the redistribution of energy due to momentum broadening or the medium response. Additionally, we can look at measurements that look at subjets to try to access the hard partons from the parton shower. And these try to separate out the soft from the hard signal so we can focus on the modification of the hard core of the jet, which is, of course, what my talk is about today. But first, I'll talk a little bit about these measurements of these hadron level measurements to kind of motivate why we wanted to move to these subjet measurements. Yeah, so first, starting with the jet shapes and the fragmentation. So Martin already gave a nice talk on this, so I won't go into all the details, but kind of the main idea is that in the fragmentation functions, we really see the energy being transferred to the soft particles inside of the jet. And then with the jet shape, we see these soft particles are located at large angles from the jet axis. And so this picture, as Martin nicely showed us, seems to be really consistent with this momentum broadening of the jet. But if you look again at the fragmentation functions, we see in a high Z region, actually, which is the region of the jet core, another effect, which is an enhancement of the fragmentation. And so here, this can't be explained by the momentum broadening picture. And so here we're really seeing hardening of the jet core. It's been explained by quark and gluons, by differences in quark and gluons, but you can see that even in these variables, we're already starting to see the physics of the core of the jet. So we can also look at these jet angularity type variables. And so I also won't go into too many details here, but Alice and Atlas have both made measurements of the jet mass. And recently Alice has made some measurements of the generalized jet angularities. And kind of the kind of moral of the story here is in these measurements, we really see little to no significant modification in these variables. And so at first glance, you think, oh, are they insensitive to these medium effects? But as Marta kind of nicely already explained to us on Monday, we really think that we're seeing a cancellation of effects. So effects like the momentum broadening and the medium recoil can increase the mass, but then we have effects of the larger jets being more modified that can decrease the mass. And so this kind of made us want to try to construct observables where we can try to disentangle these effects and really try to try to isolate different jet substructure modification effects. Yeah, so that kind of motivated us to look at these subjets to try to access the hard partons to look at the modification of the core. And so in doing these measurements, we actually utilized methods from the PP community, where these methods were designed to remove non-perturbative effects like things like the underlying event. And so in heavy ions, we do things like grooming and trimming to access the hard jet splittings. We also do things like recluster subjets within jets to access things like the parton level fragmentation. And so these variables actually have an advantage for us because they're in the perturbative regime. So they're under better theoretical control. And also they end up being less sensitive to the heavy ion background. So they're a little bit easier to unfold, and we can make some quantitative comparisons to theory. So I'll start with talking about kind of the physics of the hard jet splittings. So I like to look at the different modifications of the splittings visually using the Lund plane, because it kind of nicely separates out these different modifications the splittings can experience in like a space-time picture. And so as all of you know, the Lund plane is a 2D phase space representation of emissions inside the jet. So you end up with the angular scale, the angle scale on the x-axis, KT scale on the y-axis. Diagonals are lines of constant z, or the shear momentum fraction, and then also diagonals in the other direction are on this on the formation time. And so when we have this in the Lund plane, or sorry, when we have this in the medium, we get effects from the timing of the splittings. So you can have splittings that happen inside and outside of the medium, and you can also have effects from wider splittings that happen earlier, experience more of the medium and experience more quenching. And Liliana, I think, will tell us a lot more about this later today. But additionally, we have what's also important is effects of coherence effects. So you have whether or not the medium actually resolved the splittings inside the jet. So at the larger angles, we would expect to see decoherence, so the splittings resolve. But at the smaller angles, we maybe you would see coherence where the splitting wasn't resolved. And finally, at more lower KT, lower Z values, we could be sensitive to the medium induced splittings. And so how do we kind of access these in experiment? So Marta already kind of introduced us nicely to the jet grooming procedure. But just very briefly, what we do is we start with our jets, and then we recluster them with the Cambridge-Aachen algorithm to enforce angular ordering. And then we apply this grooming condition to access the hard splitting. And so all this grooming condition ends up being is a cut on the shared momentum fraction Z. So it's just taking everything above the green line. And so what's nice is it helps to remove the soft background from the heavy ion, the unalignment from heavy ion collisions. That's convenient. And also it removes some of the soft signal. And so we can use these to kind of isolate this hard structure modification. Okay, and so yeah, I wanted to return back to these kind of these kind of ungroomed variables, this jet angularities. So a recent measurement from Alice. Oh, my gosh, I'm going to do this. From Alice, actually measured these generalized jet angularities, and they measured them both in the ungroomed and the groomed case. And so what's cool is that so in this plot, the different colors are the different settings on the alpha on the angularities, and the ratio, the bottom panel is ratio of lead to PP. So if you look going from left to right, you can see that by applying grooming, we've reduced the systematic uncertainties, and we've kind of revealed a narrowing feature in this distribution that we didn't see without the grooming. So we're seeing that this grooming is doing what we hoped it would do, which is reducing these effects from the broadening and the medium response. And so what's also, we can return back to the Lund plane, and what's also interesting to do is make projections in this plane to access different variables that might be sensitive to different physics effects. So first we can look at the ZG, which gets at how symmetric the splitting is, and we can look at whether we see modifications to the splitting function. We can look at the RG, which is how wide the splitting is, and we can maybe access the resolution length of the medium. So did we resolve the splittings? And finally, we can look at the KT, the groomed KT, which is kind of how hard the splitting is. And so this variable actually is expected to be sensitive to the quasi-particle nature of the QGP. So whether we would have a point-like scattering off of a quasi-particle in the medium, and if we have this, it could show a KT kick that we could pick up in this KT variable. But before I go into the measurements, just mention something that also plays a pretty significant role in these substructure results, which we all know very well, that the energy loss of quarks is predicted to be less than the energy loss of gluons. And actually a recent measurement by Atlas, which I thought was very nice, showed that looking at the RAA for gamma tag jets in the pink, and then for the inclusive jets in the red. And so you see clearly that the photon jets are less suppressed than the inclusive jets. But then when we throw in substructure, we get a little bit more complicated picture, because the quark jets are narrower and expected to have less substructure than the gluon jets. And so we can get effects where the gluon jets are more suppressed and we're left with these narrower quark jets. So this is just something that can come up in these measurements. Okay, so now I'll talk about the measurements. So first the ZG, so this is looking at the asymmetric, whether how symmetric or asymmetric the splittings are. And so this measurement has been done in both ALICE and in CMS. And ALICE, it was done at lower jet PT, and CMS, it was done at higher jet PT. So if you focus first on the ALICE result, so the bottom panel is where to focus is the ratio of the lead to the PP. And so what we see is there's no significant modification to the splitting function, and to ZG, and it also seems to be mostly consistent with models. If you look at the CMS result on the right, it's also showing the ratio of lead to PP, and here we see maybe a hint of a suppression of the symmetric splittings in the CMS measurement. So maybe might ask the question, is there a contradiction here? But we have to keep in mind these are different kinematics. The ALICE result puts a high Z cut of 0.2 on the jet in order to unfold the jets. So the effect of the Z cut could be playing a role here. Okay, so moving on to the groom jet radius. So here we're looking at how wide versus narrow the splitting is. So again, focusing on the bottom panel, looking at the ratio of the lead to the PP. What we see here is actually a significant modification to the angle, where we see a suppression of large angles or a narrowing effect. So we're seeing like a narrowing of the jet core. And so this narrowing, we've compared to some models, and this narrowing seems to be reproduced by a lot of the models, despite having some different implementations of the jet medium interactions. So I'll focus on two. So the first looks at the role of the color coherence. So this is the hybrid model from Danny's in the room. And so that they have a handle on this resolution scale. So the red is fully coherent, green is fully decoherent, and the orange is just has some finite scale. And so you can see that the data, that the models with some level of decoherence seems to describe the data the best. The second model is a model with just coherence, but it's changing the quark gluon fractions. And so if you focus on the green, the emerald color, this is a model with quark only. And so you can see that this model also seems to describe the data well. And so we have thanks. And so we have two models. We had two models showing the we had two things showing the narrowing, the decoherence and the fraction and the flavor. And so another more recently, Atlas has also measured RG, and they measured this at much higher jet PT than the Alice measurement. And what they did, which was really nice, is instead of doing the per jet normalization, they made the RAA. So what I'm showing is the RAA is a function of the jet PT, and the different colors are selections on the radius. And so if you look at the orange, it's a narrower, and look at the blue, it's wider. You can see that the wider jets are more suppressed than the narrower jets. So you can ask, is this picture consistent between the Alice and the Atlas measurement despite this normalization difference? And so now I'm showing the Atlas result RA as a function of RG. And so you can see that the larger jets are more suppressed, indicating that the jets are narrower in a fixed PT. So these both results are kind of showing this narrow picture. And so finally, we can look at the hardest KT. So looking at the hardness of the splitting. And so here, the focus on the ratios, the lead to PP. And so here, it's compared to the hybrid model, which looks at the role of this Moliere scattering. And so it turns it on and off. And so you can see there is a difference in the models at high KT, but our measurement doesn't seem to be sensitive enough to distinguish them yet. But if you look at low KT, we see hints of an enhancement at small KT, which would be consistent with this narrowing picture. Additionally, Atlas has kind of looked at jet splittings, but in a different way, where they use this large R jets with trimming. And so So what they do is they take their R equals 0.2 jets, they recluster them in an R equals 1 jet, and then they remove jets subjets above, or R equals 0.2 jets above 35 GeV. And so then they get this like trimmed large R jet. And so then they look at they recluster the KT algorithm, they access the KT, which they call D12. And so they can look at the dependence on D12. And then they also look at the single subjet, which is when you don't resolve splittings. And so this is showing the RAA as a function of the D12. So they see no significant modification with the D12 variable, but they see an increased suppression for when you have the resolved splitting versus the single subjets, which could be consistent with a picture of resolving the splittings in the medium. And so, okay, so we also have jet substrate measurements done at STAR, done at RHIC with STAR. So STAR actually uses this hardcore selection when they measure their jets. So they actually select these hardcore jets with a high constituent cut to suppress the background, and then they match them to the original jets in order to regain the constituents. And what's kind of important to note is that when they made a measurement of the dynamic symmetry, and then they looked at the difference between the hardcore jets and the matched jets, and you can see that the hardcore jets are in red, the matched jets are in black, and so you can see that the matched jets, the hardcore jets were imbalanced and the matched jets were balanced. So the matched jets are recovering the energy in the jet. And so STAR has done a measurement of substructure using subjets, where in this measurement, they recluster constituents of R equals 0.4 jets into sub R equals 1 jet. And then they find the leading and the sub-leading jet within the jet, and they calculate the angle between those two jets. And so they looked at this matched AJ variable again, and they looked at it for the narrow on the left, the wider on the right. And what they saw is that in both cases, the symmetry was balanced, indicating that they weren't really seeing a modification with the angle. So you might think this is inconsistent with what we saw at the LHC, but we should keep in mind this point that March actually made at Corkman in 2017, that RHIC could actually be accessing later formation times that could have been happening outside of the medium. So another nice new measurement from Alice of subjets inside of jets is this subjet fragmentation function. So here, the R equals 0.4 jets are reclustered into smaller jets, and then all of the jets are used to measure a parton level fragmentation. And so this is the result. So if you focus on the bottom, it's the ratio of the lead to the PP. First, there's like a hint of a hardening, which is important to compare to the hadron level fragmentation that I showed previously, where we also saw this hardening effect. But additionally, this variable or this measurement is nice because in this high Z region actually is almost a purely quark region. So we could be sensitive to the energy loss of purely quarks and maybe in medium splittings here. So if you look at the measurement, you see maybe a hint of a turnover, maybe a hint of a suppression at this high Z. So it's a cool measurement. Thank you. And then finally, just returning back to these hadron level observables. So another new measurement from Alice looked at the jet axis. So what this measurement does is it has 3 different axes, the winner take all, the groomed axis, and the standard axis, and then just simply looks at the difference between the axes. And so focus on the bottom panel, so the ratio of the lead to the PP. And so this is showing the difference between the WTA and the standard compared to the difference between the winner take all and a groomed axis. And so you can see that you see a suppression of the larger delta R axis variable, which is consistent with this narrowing effect. Another thing that's interesting is that the results seem consistent between the standard and the grooming, which implies that this variable is not really sensitive to the grooming. So this is a like hadron level observable that is more sensitive to kind of the hardcore modification. Yeah, okay, and so then this was compared to some models. So first it was compared to the hybrid model. So looking at the role of this linear scattering, so similar to the comparisons for the KTG. And so this model seems to reproduce the data. It's kind of very little sensitive to this effect, but not so much. And then it was also compared to this model with coherence with a change in core Coulomb fractions that the RG was compared to. Here it's shown in the blue. You can see that it describes the data and produces this narrowing effect, like we saw in the RG. So in summary, in a lot of these measurements sensitive to the hard structure, we see a narrowing effect in the measurements that are sensitive to the angular structure of the jet. And so we kind of asked the question of this could be sensitive to decoherence. It could also be sensitive to core Coulomb effects. And so one thing that I thought was interesting, a result that came out kind of recently, was the CMS measurement of the jet charge, which is sensitive to the electric charge of the initial parton, so it gets at the flavor. And so what they did is they extracted the gluon fractions using a Pythia template fit in PP and in lead, which is shown here. And surprisingly, they saw no modification to the gluon fraction. So I thought this was interesting because this could possibly indicate, that we're seeing this narrowing is due to these decoherence effects. But then, of course, when we think about this narrowing, we can't forget about this survivor bias that we've already actually had a lot of conversations about this week. And so the survivor bias is just the idea, the fact that when we compare the final modified lead jet, we compare the final modified lead jet to the unmodified PP jet, and instead of comparing the initial unmodified jet. And so what happens is that you have this bias where at a fixed jet BT, you're left with less quenched, narrower jets. And so, I mean, we talked about this a lot this week. It's been talked about for years. There's many papers on this, but one more recent result, actually from Danny and Conrad in the room, so I hope I explained it okay, is looking at this effect on RG. So what they did is in their model, they did what we do in the measurement. So they took the final energy selection for the jets, and they reproduce this narrowing effect. But then when they actually take they look in their model for the initial energy selection, instead of the final energy, they actually remove this narrowing effect for the more quenched jets shown in the blue. And so we have this narrowing effect, but we have the caveat of the survivor bias. The second thing we see is little to no modification of the splitting function. Here we have the caveat that maybe we're removing the n-minium splittings with the grooming, although the subjet fragmentation seems to maybe be sensitive at high Z, so that's something cool to maybe remeasure in the future. And finally, these substructure variables don't seem to be sensitive enough to measure this molar scattering, but I think Peter will talk a lot about this later in the acoplanar measurements, where you do maybe see some sensitivity to this. And finally, I give a lot of caveats here, and we see Raymond's talk next for hopefully some solutions in the future for some of these things.
Thanks a lot for a very nice talk, Laura. That was a super nice start of the day. So let's go to some questions. Peter is first.
Thanks, Laura. This is like a really nice overview of a massive amount of data. I want to focus on this RG and actually both the Alice and the Atlas. And as you're talking, I was trying to understand. There's a slide, first slide 13, and then slide 14. So let's just kind of look at what Alice sees as far as RG goes and then look
Yeah,
at the
there
atlas.
they are next to each other.
No, let's do with 13 first. The Alice result.
Sure.
Right. So just characterize this as so the medium effect is a shift from large RG to small RG.
Yeah,
So
exactly.
now let's go to the atlas measurement, because as you were talking, I realized I don't actually understand what was done. Maybe this is a question of the atlas guys.
Yeah.
So let me say what I think was done, and then we'll find out what really was done.
Sure.
So what is RAA? RAA is a ratio of two quantities in PP and lead. Is this the ratio? If I choose any RG bin, 0.26 to 0.4, are these jets, the rate of jets selected for the same RG interval in PP and lead?
Yes.
Right,
Exactly. Yes.
right. So what does it mean then larger jets are more suppressed? It means RG has gone maybe RG jets don't disappear, they go somewhere. So if we think about the Alice, it's all the distribution is shifted to smaller RG. I think what this says, it's moved out of this bin.
Yeah.
But you've got another axis now, which is RG. So it can go somewhere else. It's just not tabulated in the right way. Wrong statement. It's just not tabulated in the way this plot is made. So is it the case that in fact the message from the Alice distribution, which was measuring the shift in the distribution, are actually the same?
Yeah.
Is there independent information here?
No, so I think this adds information to what we saw, because what we saw is like a per jet normalization. So just because we saw this enhancement doesn't mean that there was an enhancement. It could mean that it could mean that there was less wide jets, lesser narrower jets, but the effect was higher on the wider jets. So overall, there's more the fraction of narrow jets to wider jets is larger in heavy ions than in PP.
That's what
But
the
in
Alice,
the Alice measurement, or
that's
at
the
least
Alice plot
my
shows.
thought would be
Mhm.
that it's something like this.
Yeah.
The narrower jets are still suppressed just because of the way we normalize it. We get this feature. So
I'll let it go. I guess I get stuck on your large jets are more suppressed. That I stumbled on that. So I'm not.
I mean,
Yeah.
they're in a fixed PT bin, they are more suppressed. So that would be a better way to say it. Yeah, which yeah.
So I was just going to agree with what Laura was saying. I mean, we know that suppression we know that the jets at a fixed PT are suppressed, right? We know that the overall RAA is much less than 1. And so I think what this does is it adds another dimension, right? The jets are not just shifted in RG, they're also shifted down in PT. And so you should really think of this as a 2-dimensional problem.
Yeah.
And that's what the Atlas results add, I think.
Yeah. I think, yeah. So there's James in the front.
Yeah, so I actually think it's not new information, because there's a normalization difference, but it's one number, which is the jet RA, and jet RA has been measured, right? So, I mean, it's a different way essentially of plotting the thing. But the only difference is within this Atlas measurement, it's kind of both measuring the RG and the normal inclusive jet RA in the given PT bin. We already know that number, right? I mean, it's nice to see kind of plotted differently, but there's not really an extra observable that we didn't know before. They have, it's a beautiful measurement. I'm not saying that at all. And they have the PT dependence. I just mean this absolute suppression, the only new thing being added is the jet RA.
I guess, but the wider jets could have, the suppression effect could be larger. So like what you would extract from the outer RAA could give you a larger suppression. I mean, like a larger effect. So like I see what you're.
I mean, so I mean, there's just each bin on the right here is some PT interval.
Yeah.
All right. So if I had next to that a plot of the inclusive jet RA as a function of PT, I just look up what's the number of jet RA, and I scale up that plot on the right, I would get exactly the same normalization as the one on the left.
So I think we have time for one last.
This is just a general comment. I mean, we know that every time we look at modification, we do ratios. I mean, that's one way to look at it. But in the meantime, if you look at the fragmentation function, the ratio is sort of enhanced for soft particles.
Yeah.
But if you look at absolute fragmentation function, the soft particle dominate, right? You know, so this means that most of the energy is carried by, you know, the enhancement or whatever. The extra energy goes to the soft particle. But once you do like a jet shape, the ratio tells you a lot of suppression at the high, for example, at high Z, the little bit enhancement probably low end. So another complementary way is to take the difference between AA and PP, and there you probably have a better idea where the most of energy move to.
Yeah.
Because the ratio does not really tell you this information.
Yeah, and I think like a lot of these measurements with the fragmentation and the radial, the people who did the measurement should correct me, but a lot of those do look at the difference as well. So I think that those also exist. That's a super good point. Like, yeah, I think that, yeah.
Okay, I have a last comment, but it's just to go 2 slides back.
Sure.
Allow myself to do. So yeah, so I just wanted to say a bit of warning when kind of classifying models in this kind of way, because I think it's kind of convoluted. So I know that, for instance, that in the hybrid model, of course they have the bias effect, right? Of course they're losing jets are losing energy, and of course they have the quark-gluon fractions with the Lund Plane. So it's not only the role of color coherence that drives this effect, right? And I don't know exactly what this Yuan et al. is doing, but I'm guess also it has some of the same elements. Sure. So I think we are starting to reach an agreement. I mean, a kind of common understanding that most of the effect is probably due to this kind of bias effect, survival bias. But the amount of it, and that's what we see in Danny's curves, right? The amount of the bias is given, for instance, by color coherence effects. Or in other words, yeah.
Yeah, no, I think that's a super good, I think that's they're very close, yeah.
You have a comment on that, Matt?
I asked this question before, so I guess maybe in the discussion we can come back. Well, okay, I didn't ask it here, so we will maybe discuss it in the afternoon session. The picture that is shown right in the middle have some arrows between some arrows, and it defines some sort of characteristic opening angle. And then we know that the radiators, interact coherently with the medium if they are close to each other. So the green arrow, and they start interacting incoherently if they are a red hour apart. Can we make that connection now with the data? It's it's a question to theory.
Yeah, so this is what we see in Paul's model and Danny's model in our calculations, that the amount of bias depends on whether you have that angle or not. Whether you quench as one single subject, which gives you kind of 1 power of REA, or whether you quench it as 2 subjects, which will give you REH squared somehow.
But this is medium property, so you should be able.
Yeah. So the
data, you say that.
Yeah. So
average distance between scattering centers is something. Can I read it off?
Yeah. So for instance, you can read it off in the amount of bias, right? The amount of suppression on the right hand side and the enhancement on the 0th order reading of this, right? Is if you would quench all the jets incoherently that happen to be inside the medium, you'll get a huge effect.
Right.
If you have some kind of color coherence effect that you moderate this effect, you don't quench all subjects, then it's a less effect, right?
Well, you have to put RAA on this, right? Because
sure, yeah.
Jets are suppressed.
Yeah. I'm talking about the relative.
So you can do it. You could do the same thing there.
Or there. Yeah. So in a sense, this
So
could.
you say your model, I can read off what the lambda is, the mean distance between scattering centers. So that
No, not the lambda. You could start telling something about how many jets are produced inside the medium. and by produced inside the medium are jets that are resolved by the medium. Say like this.
And in the medium with the properties that you put in your model. So
Right. Yeah.
Basic question, how do I get from this measurement to medium property?
Well, if you tune on RAA for inclusive RG,
Okay.
then you tune your Q hat. Let's say, again, super simple model. You tune Q hat. The only lever you have is this phase space.
Okay.
Right. The only lever you have is to say either I quench all my jets or I quench such a subset of them, or all my subjets in the jet or some right? All my partons in the jet or a subset of the partons of the jet.
So are we done?
No, yeah, well, not yet, but combining all these things could give us definitely more information. Yeah, we're almost there. No, but should we have one last comment, and then we...
There's a question. So these have both the WTA minus E skin and theta G measurements, and they basically show very similar picture. And have you made the correlation between these two variables? Are they just identical variables, essentially?
We have not made the direct correlation, although, I mean, you show I mean, Ray made the measurement, so he can answer better than me, but we do look at the difference of the grooming effect on it. So that is related, but no, the direct correlation I don't think has been made. I think they are, yeah.
Okay. Yeah. Yeah, I think we have to cut
Yeah.
the discussion. Thanks, Laura, for really exciting and